Welcome, everybody. Today we're going to talk about how to get started with laser plastic welding. Spoiler alert, Superman is not involved. I am Jason Dornboss. I am sales manager, and with me is Nick Flesher, our director of innovation and development. And I want to start things off with a question. First off, why did you sign up for this webinar? So this is actually we're going to try this. We're going to do a poll. And so you should be able to type in. Oh, it's taking forever to spool up. Is it? Oh, yeah. Okay. It's on. It's live. It's live. So type in your response in this poll. Why did you sign up for this webinar? Do you use laser welding all the time, but you just want to learn more? You're curious what laser welding is? There could be a lot of different answers here. So just type in your thing. Why did you sign up for this webinar? I want to know.
2 responses, and I'm one of them. And my answer was because Jason invited me.
Nice. So I'm going to say
that will not be visible, right? So people can answer that.
I said presenting. Did you hit enter on what you said?
I did, but
mine's. Oh, now there's 3 responses.
Yeah,
here we go. Anybody else filling up 5 responses?
You can answer that throughout the webinar. So
yes. All right. So
that feedback.
This is helpful for us because then that'll guide how we talk about it. Looks like some people are answering the question in the chat. Looking at implementing laser welding in a new design. Great. I have a lamp that I don't think vibration weld will work. Oh,
yeah. Very common.
Yep. We'll talk about some of those things. All right. I'm going to give an overview of Xtool so that if you're not as familiar with who Xtool is, this will help you understand why Xtool is presenting about laser welding. Like, what do we know about it? Xtool solves complex manufacturing challenges. And if you look at our logo, the X in our logo can be viewed as a chart. On the left-hand side, there are companies with plastic welding expertise. And on the right-hand side, there are companies with custom automation expertise. What we've found is that plastic welding providers, while they do a good job with providing plastic welding experience and good plastic welding solutions, they don't do well with custom solutions. So you're stuck with whatever box they've built, and your application needs to fit inside the box. On the other side of the spectrum, custom automation companies, they lack plastic welding expertise. So they can tailor a solution around your application, but they don't have a lot of plastic welding experience to make that solution high performing. They need to rely on the expertise of another entity. Xtool is the best of both. We have both plastic welding expertise and custom automation expertise. So you get the best of both worlds. And you get a configurable plastic welding solution that is optimized for performance. It also means that when you have an automation solution with plastic welding inside of it, and if we've built that solution for you, there's no finger pointing as to who's got to figure this part of it out. It's all one solution from one experienced provider. We have engineering services, plastic assembly technology, and custom automation. These are all things that you can take advantage of. Engineering services includes 3D printing. We help you with development of your plastic part design. We can help you with prototyping. If you are creating prototypes and you need to weld them, we can weld those for you in our lab. We can help you with validation. If you have a design and you need to prove it out, we can help you with the validation because we can do some testing here. We've got a lot of different plastic assembly technologies. We're, of course, going to be talking about laser welding today. And then the custom automation experience we have, we can provide fully automated solutions where there's no human interaction. It's lights out automation. Semi-automation, where it's somewhere between fully automated and a standalone machine where an operator is loading parts and taking them out after each cycle. And then we can provide integration packages, not just for staking, which is what's shown in the slide, an integration module of InfraStake or NanoStake are very common. People are pretty familiar with, I can integrate this. We can also provide integration solutions for all of our plastic assembly technologies, laser welding included. So if you are a custom machine builder and you need that expertise from somebody, we can help you with that. And we believe we're the best partner for that because we also have custom automation experience. And so we know how to tailor that integration offering to fit a custom automation line. Are there questions coming in right now? Or are these people still telling us?
Got good answers as to why they are joining a couple new projects, designing considerations, looks like bringing it into their organization, and Duquesne Laser Welder, which we'll get into the types of laser welding in a moment.
Yeah,
we're familiar with them as a competitor, of course, and they use the same type. So I think this webinar will translate well to the type of technologies that
awesome.
we both do.
So on a scale from 1 to 10, and this is not going to be a poll, this is something that I want you to put in the chat. Just put a number. How much experience do you have with laser welding? 1, what is laser welding? All the way to 10, I could teach this webinar myself. Maybe I can give you presenter controls and you can take it from there and I can back away. Just go ahead, rapid fire that. We got a 6, a 3, 1. Lots of 3, 2, 1. This is good. Good. So we're going to be able to educate lots of people.
Yeah, and this is really helpful because it allows us, we have various degrees of webinars. This is kind of an entry, how do we get started, obviously in the title. So this is excellent. We'll kind of keep it general and high level, and we can go as deep in this via chat as you want or offline as well.
Make sure that you are asking any questions that you have as we go along. We'll have time at the end for questions, but we want to take those questions throughout. So if your question comes to mind, put it in there and we will do our best to answer it right away.
Okay, great. Let's see, Jason, can I advance?
Take control and you should.
Yep.
All right,
fantastic. So we're going to cover kind of the basics first, and we'll go a little deeper as we go, and then we get into a little bit of our version, our flavor of laser welding, how we implement it. The process itself is really quite straightforward for through transmission. We're going to talk about a different version of welding a little bit later. Through transmissions, probably well over 90% of the market. It's a 3-step process where you clamp, you heat via the laser, and then you cool, you cure. This looks different for every single application, obviously, but at the basic level, these are the 3 things that you need. The heating process, which is kind of where the magic happens. Well, actually, all 3 are critical. The laser is transmitted through a top transmissive layer. And that can look a lot of different ways. We'll go into those details. Clamping is critical. Tooling is probably a lot of customers that come to us and they maybe have a laser welder and it's not running quite properly. Tooling is most often the culprit. You have to have what's called intimate contact. And the reason for that is the heating process conducts through the the transmissive layer into the absorptive layer. The absorptive layer then generates that heat, and the clamping provides conduction to the upper mating component, if that makes sense. That's with the 1 micron wavelength. We're going to kind of showcase wavelengths in a little bit later, but essentially this is the process. And then cooling is kind of required with friction welding, IR welding, hot plate welding. You've got to have a cure phase for those plastics to sort of re-solidify. 3 key elements, kind of skipped ahead with that a little bit. Intimate contact. 2 is really kind of split into 2 parts, IR transmissivity and absorptivity. Both are important, right? If there's one thing that's kind of I won't say challenge, but something to be mindful of with laser welding, it is you have to make sure you have transmissive and absorptive components. So just a part of laser welding that's really important that you have to be mindful of.
The laser has to be able to get through one layer.
That's right.
Yeah, that's right.
And then compatible materials. Just like any plastic welding technology, you've got to have materials that go together. Most commonly, we see they're the same material type. If you're in the PC, ABS, PMMA family, which someone mentioned lighting earlier, that's totally fine. We have a compatibility chart on our website. You can go grab that. and have that as a resource if you like. Just to kind of show what this looks like, and there's a lot going on. We'll play this video twice. There's a lot going on in this video because we actually implemented other auxiliary functions in this video. It's a 2-cavity tool, so I'll go ahead and play it for you. All right, so what happened there? You saw the press come down, created that intimate contact between the two parts. These particular components in the 2-cavity tool, you'll notice one is natural, one is black. That doesn't have to be the case. There are transmissive properties, and actually we'll show an example of that a little later. You'll notice that as the laser we used a different filter. The 1 micron wavelength, which is what we're using here, is invisible to the human eye. So you can only see that through the camera that we're using to showcase that. It's moving really quickly. So it looks kind of intermittent, but the camera is just not picking up on it. We're moving like 3,000 millimeters per second in this particular application. Once the cure phase happens, the whole tool flips up. That's because we implemented a laser marker in this tool. If you're wondering if we could use the same laser for marking and welding, you can't. It's kind of like using just 2 totally different size lasers, essentially, is why. One is made to mark, the other is made to pour a tremendous amount of heat into the part. So they're 2 very different functions.
It's like a bazooka.
It's like a bazooka or a rifle, basically. So the 2 very different functions. And then this particular customer implemented in retrofit in the field, we implemented a through conveyor on this particular machine. So every part that was good went to the left, every part that did not meet melt criteria or seal criteria kicked to the right. Any questions on the process? I said I was going to show it twice, Jason. I'll do it again. It's 45 seconds. So
if it doesn't play for you, you can click play on your screen and it should go. Great question, Ron. Yes, during the cooling process, we maintain clamping. You have to keep holding while those materials are cooling down so that they form a strong bond.
And I'll go so far as to say that clamp pressure, we actually have 2 different pressures in our process, is really critical. We've seen situations where maybe there's like a hard stop implemented, as we like to call it, either within the part or within the tooling, and that's not acceptable. Another great question is a fan used for cooling. No, we typically don't. It's not usually required. And really, we find that you only need 2 to 5 seconds for laser welding. So it's really quick. How much meltdown? Excellent question. It's really small. If you're familiar with vibration welding, you're moving multiple millimeters, and laser welding, this particular application, I think was 0.6 millimeters. And that part's approximately 6-7 inches long.
Yeah.
So it's really precise. We're actually going to talk about that. So excellent question. What was the vertical?
Laser etching.
Oh, laser etching.
Yeah.
And then this particular customer used that as a part reject if they didn't meet melt depth, which didn't happen very often. Yeah. It was just in case something was misloaded or whatnot. So excellent question.
Flipping
guys.
up was not. You don't have to flip up in every application. No. We just simply did that because it lent itself to that.
I think that's the only time we've done it.
Mm-hmm.
And we even done laser marking in the same sort of zone, so you didn't have that complexity. So obviously added complexity in that tool that the customer actually found was required because they were doing 2-cavity. I'm going to talk about 2-cavity in just a moment. It's a great cost savings tool that honestly we don't see a lot of our competitors do, and we've learned some tricks to that. You can do it poorly, so we'll come back to that. So as far as different machines, equipment goes, how we implement laser plastic welding, this is a good sort of showcase of an application we did. So I'm going to show this video as well. I see, do you need to clean the parts before laser welding for contamination? That's a good question.
How dirty are they?
How dirty would be the question, the answer to that question with a question.
Yeah.
It does need to be relatively clean. We have seen, especially for like those were natural nylon, you do need to have clean parts and not have particles on them or they will burn. So you can still get good welds, but that burn might over time create some challenges in the tooling.
Yeah.
So again, we typically as plastics joining people, not specific to laser welding people, we do that, but there's pros and cons to every single technology that we use. And laser welding, super fast, super clean. But some of the cons are you got to make sure you've got good transmissivity in those parts, and making sure your parts aren't terribly dirty is a part of that process.
Yeah.
What type of maintenance do you recommend? It depends on your process. If the process is really clean, this video I'm about to show was
Filter.
It was a filter application, and the process was really clean. There was no off gassing. No smoke, no particulate, nothing. So from a cleanliness standpoint, there wasn't any maintenance on tools. We have had some customers that maybe have a little dirtier molding process, and they might have to wipe the glass once a week. Well, maybe more frequent than that, but that's really rare, I would say. For laser welding, if it's producing off gassing, something's off.
Yeah.
That's how we say it, basically. So I'm going to show this video. This is kind of a cool application where, and I don't know if everyone can hear me while I'm playing the video, so I'll explain, and I'll just show this one once. It's a 2-weld application because we're welding a filter to a housing and then a cover to a housing. And then there's other stuff going on too. I'll pause one more thing. You'll see empty nests, and that's because we're protecting our customers' parts on this. So we pulled those from the nest. So. All right, let's get back into the technology a little bit. Those are just a couple of examples we want to show a different part of the process on video 1. Video 2 is just different ways you can think creatively around that. We did a lot of things on that second video for cycle time. The customer had throughput. So for example, the 2 lasers happening at the same time, you notice the annotation on the video. Yeah. That was because we needed to put a lot of power into the part, and we didn't want to burn, so we sort of broke the power out into two lasers for that. So we'll talk about selection of equipment in a minute based on throughput, budget, things like that. So just to sort of educate you at a wavelength level, I threw that out a couple times. 1 micron is what most of the industry uses. These images are to sort of showcase what's happening as you're applying that heat. Okay, so that clear material that we talked about, that transmissive material looks clear here. And you can see the lasers passing through. We're showing not much heat's really absorbing into that. And then the heat absorption into the second component is really isolated. So it's super thin. The heat effective zone, if you're familiar with that term in plastic welding, is really narrow. The collapse is really small. If you're collapsing more than a millimeter in laser plastic welding, you're melting a lot of material. And then the second wavelength we have here is 2 micron. There's different, depending on what supplier, hopefully not outside of Excel, that you're working with. These might be off just a little bit, but generally, 1,000 nanometers. We use 980. Is classified as 1 micron. 2 micron is 1940. And how this works and how this process works, typically clear to clear, larger heat affected zones. So that's a bit of a con, but you can do clear parts. So that absorptive comment I've said a couple times can be transparent, can be naturally transparent. So a lot of clear materials get put into this classification. And what's happening is some of the heat is being absorbed into the upper level. You still got to have intimate contact, still have clamping. And then it passes through around 70%, and another 30 to 40% is absorbed into that lower level. And then as you can see here, the rest of the energy is dissipated. So pretty nichey, right? Like I know there's someone mentioned lighting.
Yeah.
If you're in the automotive space, you're probably not dealing with clear to clear. The medical space uses this quite a bit. Consumer products sometimes. So just be, you're here to learn, and that's just one thing to be aware of. 1 micron, 2 micron, totally different methods of heat transfer, and that's why. I mentioned the conduction in this 1 micron wavelength into the upper, and that's what generates the heat, not the laser in the upper transmissive part. That's not the case with 2 micron. Some of it's absorbed in the upper, some absorbed in the lower, and then the rest is lost. Questions, comments on that before I bounce to sort of a different method altogether?
And the reason why the 2 micron is absorbing more is because if you look down at the molecular level, the longer wavelength, like 2 micron is longer than 1 micron, that longer wavelength just gets absorbed by the plastic more. Yeah, differently.
Yeah.
And so not all of it, but some of it gets absorbed, and that's why it can, kind of heat everything as it's hitting it.
I'll say to all of our attendees here, you don't have to know what plastics absorb what. We've got an applications lab, that engineering service piece that Jason recommended, has applications engineers that can say, okay, well, your weld design is this and your materials are that, and we'll work with you on that. Okay, so don't be scared off by that. That's just part of laser plastic welding. We wanted to share it, and we can work through different constraints on that. If you're sitting there thinking, I've got a little bit of glass content, maybe you've got a PA 12 with 30% glass. Well, how does that affect it? The answer is it does. And it means that the designs need to be a little thinner, and the glass content needs to be pretty homogeneous, pretty well mixed, evenly mixed. If you have sort of a glass concentration in one corner, you hit glass, with fibers going all different directions. It takes that light and disperses it everywhere. So you might get a cold spot in the weld. What's the weld strength level? Excellent question, Oscar. We always say it depends. We typically want to see 80 to 90%. Most of the time, parts are breaking in different areas. So we call that parent material if we're doing like a burst test. If you're doing a tensile test, we want to, our target's 90%. 100% is not typically that likely. Mainly because when you do hot plate welding, you can hit 100%, but that's because your flash gives you more strength. There's not much flash here. We've had glass content parts, high glass content. They might get down in the 60 to 70 to be real honest. So something to be mindful of when you're designing your weld rib, you might need to go with a little bit wider weld rib. And the answer is it always depends. What strength do you need for your application? Because you're going to lose a little bit of strength with welding, right? So I want to be mindful of time. We've got a few slides left here. So direct laser is using either of those two wavelengths, and you're kind of opening the parts up so that the face of the weld ribs are open, and applying the laser to both to generate heat, just like non-contact infrared welding, and you put the parts together. So kind of goes like that, from this to this. We have a video, I think, for this, right?
Yes.
Yep. We got a video for that later, so we'll show you that. Be mindful that you can use mirrors. If you've got a round part and you're thinking to yourself, okay, this is great, but I can't really apply the laser the way you're kind of showcasing here with through transmission, you can design a little bit of a taper, a little interference fit, and bounce the laser off, as Jason's very skillfully designs here, and hit the part radially. What I'll say to this is we have seen customers struggle with properly designed mirrors. We use optical engineering or optical software to make sure we can design those tools correctly. This was about a 6-inch part here you see on the left. Kind of see this little shiny black portion. That is a weld rib. So be mindful of that. You can do that with 1 micron or 2 micron. Here's another custom example where we use mirrors and we were actually kind of getting up inside the part. We've got our customer's parts blurred. And this one is a really highly precise machine where we're heating both surfaces, and we used a servo system for really precise force control. We were using infrared temperature sensing to make sure that we were hitting the temperatures we wanted to. And we had quick change tooling, which you can see here. So we had 2 questions.
A couple questions about materials. So glass fiber, like, is there limitations to percentages? And is there issues with mineral fillers and flame retardants and transparency, all those things?
And what? That's a broad, a lot of specifics in that one question. I would say there are limitations to each one of them, right? Colorants, white is typically challenging. You can design different colors that are IR transmissive, and you have to have good absorptive content. So we typically see carbon black in the absorptive content. So the answer to the question is yes. To get into the specifics of how, I think probably makes sense to continue the conversation. Amorphous and crystalline both can be laser welded. Weld quality and strength, I would say application and weld geometry dependent. How planar is your weld need to be? Oh, nice question there. The answer on that one is how big is the part? So if the part's a little bit larger, we can probably, if you keep it 2D, about 3/4 of an inch is how planar needs to be. That's only if you use one laser source. We can use multiple sources and scanners. I'm going to explain the type of welding here in just a second. For quasi-simultaneous, what we use most of the time. Size and part limitations. For quasi-simultaneous, it's typically, wow, that's a tough one, because we've done larger multi-scanner. 16 by 16 inch is pretty straightforward. You get outside of that, we can do it. It requires a different sort of mindset and take. Is there a handbook which explains what laser welding concept?
There probably is. We don't have one.
We don't. We use TWI's got a plastic welding handbook. We use that for some references. It's a big old thick book. We've got tons and tons. We've got design guidelines on our website, compatibility, probably half a dozen or up to a dozen webinars. So we have higher complexity, pros and cons of laser plastic welding, myths, things like that. So I'm going to keep plugging along. These are great questions that we probably are going to need to follow up with you all on. I want to make sure I explain this concept. So in the laser plastic welding process, there are multiple versions. I would say for us, 90% of the time, so we talked about through transmission and direct. Within those, there's the categories of quasi-simultaneous, where you're going around really fast and you're displacing material while you apply the laser.
And that's what was in those videos.
That's what was in those videos. Great, Jason. Contour welding can be done with bigger parts. So someone asked about the size of parts. There's really not a limit. You could do, say, like a light bar across the back of a tail lamp vehicle with an XY gantry, and slowly move that laser while you're applying force with contour welding. The challenge with that is one continuous path. You're not going to go around probably a second time, and you're going to have a high spot and a low spot. So you gotta do some process tricks. It's typically pretty slow because you have to go around and every single spot's got to get the laser energy while you compress, and you build some internal stresses in when you do it that way. Line beams another way. We through optics, we sort of spread the beam out. These are typically for smaller, intricate parts, maybe larger flat surfaces as the weld goes. You can do masking if it's really, really small. Measure weld strength. We typically do burst testing or tensile testing. So I think ASTM standard would be how we do that. Yep. We just want to show a quick video on direct laser. You'll see these parts blurred out for customer confidentiality.
But you'll get the idea.
Yep.
How do you optimize the laser energy to prevent plastic degradation? Well, that's the magic.
Yeah, that's what you want to try to not do. This video with direct laser, I would say, is a good question and good timing. You'll notice the smoke happen. This is a nylon application. This was less than ideal. They designed it for ultrasonic, and then the ultrasonic suppliers said you can't do these parts because of what's called far field welding. I'm not going to go into that, but essentially they were stuck. It was nylon. You can't really do hot plate welding. Vibration, too much particulate. And so this is a really clean nylon weld. I would say plastic degradation is typically caused by oxidation. So you want to make sure you don't overcook. If you think in terms of cooking the plastic, you want to apply just the right amount of heat to get the plastics semi-molten, not liquidy, not heated, and not oxidized. Those are kind of the things that you want to do.
You can kind of think of it like, I think cooking is a great example. Like if you have your grill super hot, 900 degrees, and you throw a steak on there, it's going to sear the outside, but the inside's still cold. Same thing with laser welding. There are different parameters, and we have a slide talking about the different parameters that are available. And those you can adjust them to try to slow your rate of heating.
I'm going to skip this slide. This is basically just more wavelength nerdism.
Yes.
So when do you need laser plastic welding? I hope that most everyone on this call this webinar is asking that question. We sort of have three categories: clean, no particulate, in some cases visually appealing flash, and usually I'll say no excess heat. This is for reference. This part is a 1 1/4 inch sample plaque, and you can see how tight the flash is. There is no technology that is flash free, but laser is about as close as it gets. So clean is number one. Precise is number two. This is a smaller part. We know that not many people have parts this small. It was smaller than a dime, and we had a beam spot of I think it was actually 0.5 millimeters on this one, and we were collapsing 0.08 millimeters. So super precise, and we're doing that weld in 2 seconds. And then fast. It's really focused energy, so you're putting the right amount of energy into the right location instead of other technologies where it's kind of going everywhere. You can have small parts in the sub-second weld time from an energy on standpoint. So clean, precise, and fast is kind of the way that we say it. As far as like what filters, what do you think you might need laser welding? I've mentioned materials numerous times in this webinar. This is just a visual to show, this is the same part, the black polycarbonate. It appears black. This is just to showcase different weld rips. We have these sample plaques we could show you if you're interested. And this is a laser inspection system we have. So it's using the same wavelength lights and filters on the camera. And you can see how it looks like it's completely transparent. If you're wondering if we could do end-of-line inspection with laser welding The answer is yes. So different than a hot plate welding or a vibration welding, because the laser's got to get through that upper layer, we can use some off-the-shelf vision systems with some of our experience around the laser wavelengths and show that you've got a good weld non-destructively during the process. I will say the big caveat to that is glass content makes that really hard to impossible. So there's a big asterisk on that, and we would prove that to you before we go. I'll often quote it. So process parameters. Jason alluded to this: force, laser wattage, weld depth, laser focus and path, number of passes, and the speed of the laser.
Yeah.
Those are kind of the big levers that we fill.
So I think this is a great place to answer this question. You previously mentioned that we talk about intimate contact. During laser, you heat the parts. Does that cause bow and twist on the parts? And I would say the answer is no.
No.
In fact, most of the time from molding, parts are warped, right? Plastic parts don't come out of the mold perfectly flat. They are warped.
What do they do, Jason?
I mean, yes, everybody's parts are flat. And we're able to the clamp force of the laser welder is actually putting those back to where they belong. And then we hold them there while we do the welding. And we're holding them, we're welding them, and they come out maybe flatter than they were before they went.
That's true. I'll also say that sorry, I just lost my train of thought. During laser welding, you heat the parts. Oh, I was going to say, the laser is so precise, right? I mean, what it's doing is precisely applying that heat. We've seen you could touch adjacent to the weld rib by less than 1/4 of an inch and not feel the heat. You put your thumb on the part itself, it's hot. So from an energy standpoint, you're putting the least amount of heat into that part with laser welding, and yet still get them to weld.
Yeah.
So configurable laser plastic welding that meets your needs. That's kind of our place in the market. These are just 4 different examples of the kinds of equipment that you might need. Jason alluded to this earlier with our sort of logo and who we try to be in the marketplace. This was sort of a lights out, not fully because operators still had to load the parts. This one was a lighting application, right hand, left hand, to minimize capital. And we actually did 2 parts at a time in this one. This was quite a complex machine, but we were drastically more competitive in terms of 1 piece of capital to do right hand, left hand, and part A and B in that right hand and left hand.
So you can load the parts while it's welding in the background.
This is more closer to what I would say one of our standard versions is, but this actually, I'm going to show you what was inside this in just a moment. And then Jason alluded to integration packages. This is a nice package that we can offer to, if you've got a machine builder of choice, that we can implement a lot of that laser plastic welding expertise and process development with that machine builder.
And again, I want to iterate that these are examples. So
yeah,
for example, that integration piece, you might look at that and go, how wide is your integration piece? And the answer is, how wide do you need it to be? We would design that integration module around the application and how you plan to use it.
That's right. Yep, definitely. Good question. Required to go to annealing oven. I would say no. I mean, I have never heard of that. I have heard of it with vibration welding to go to annealing oven. I have not seen that, because you're just not putting as much heat as you are into vibration. Is excellent if you can submit your weld to your plastic parts, not be as concerned with dust, and you've got all the material in the world to play with. Laser is not that. It's just it's a totally different tool.
The other question on here is, does the time duration of plastic part exposure to laser energy a parameter? So you can weld by time.
Yeah.
We typically don't. We typically weld by, we're measuring the collapse of the part.
Yeah. Yeah. We that's sort of a closed loop and parameter where if you're welding by collapse, you can weld by time, weld by passes, which is kind of like time. But I actually only know of one work application. I mean, we've done dozens and dozens of applications where it's weld by collapse. The reason for that is you can accurately predict how long it should take you to get to that depth, and our systems have alarm limits on those. So if you get there too quickly, something changed in your mold process. If you get there too long, probably the same thing. So yeah, mainly it's by collapse. I think we've got one more slide here just to wrap up. We really lean on how do you arrive at the right solution. Okay, laser plastic welding is not the cheapest technology. So we acknowledge that and we say, well, what do you need? Do you need a lower power? Is budget driving it, or is it speed? What are the sort of criteria you need to meet? Tooling features, do not underestimate this. If you're starting to get into laser plastic welding, we actually have a patent called laser lock, which is kind of a way to hold your parts a little differently. Progressive tooling, meaning if you're like, man, that's an expensive technology, we find ways to put the same, maybe a weld 1 or weld 2 in the same machine. This is an example of that, where we're welding 1 cavity and 2 cavity, and we're actually monitoring both parameters. So your budget will drive, well, how complex is the tool? How low can your power be? And then, can we implement some auxiliary functions in there to maybe eliminate a piece of equipment? So, great question. Does it work? The principle, the more powered laser, the better is the welding. Absolutely the second. You can't have overheating. So, you need to, that's actually why we broke up the laser you saw in the video into 2. We had 2 500 watt lasers instead of 1,000 watt. It's not uncommon where we're in the 100 watt range from a budget standpoint. It just might take longer to get there. Mm-hmm.
So yeah, you can apply too much energy too quickly and have a bad weld.
That's right. Yep. Good questions. So, a lot of information in 40 minutes. Jason, you can feel free to actually.
Yeah, I'll take control.
Yeah, there you go for the last slide.
This is the last slide, but we can jump back to wherever you guys want. I know a lot of questions were asked during the presentation. Hopefully we answered them. If you feel like you still have a question, go ahead and drop it in there again and maybe word it differently if we didn't quite get to the heart of what you were asking. We can also follow up with you after the webinar and have a meeting discussion. Here's a question right here. What is your process for material compatibility testing? That's a great question.
It's a great question. Sometimes we can use our own sample plaques. We've got pretty extensive set of sample plaques. Sometimes companies, if you're working with material compounder that you're saying, I'm going to be using these for laser plastic welding, that actually kicks them in a category they know. We've got a number of companies we work with that, and they'll give you samples, and then we prove compatibility.
Yeah.
From that, if you've got time and you're that thorough, that is what we want. We can literally determine, you don't need a 400 watt laser for this. You need a 200 watt laser, and we'll hit X linear inches at this width and get your cycle time. And we pre-engineer it basically based on those samples. So we typically, to answer the question, we typically test it though. We want to make sure we're being thorough on.
Yeah. We just did this last week with a customer. They had a very specific material that they wanted to check the compatibility of, and they had plaques made by their material supplier, and we put them in the welder, welded them up, did tensile tests, and iterated and got it to the best we could, and said, all right, here's the parameters, here's our best cycle time, and here's the strength that we achieved.
Stephen asked also about 3D printing materials. The tricky part with that is you have to have transmissive properties, and most of the 3D printing folks don't care about that.
Mm-hmm.
So, for example, we do HP multi-jet fusion, which is a really sort of next level in 3D printing. It has inherent in it an IR absorbent. I'm trying to say that. And so, actually, I think our cover page we did a laser cut transmissive component for that. So tricky to use 3D printing, obviously
The absorptive can be 3D printed, but the transmissive usually can't.
Yeah, we had a question about metallized components. We can do so if it's just purely metal to metal. We don't play in that space. The wavelengths are different, the powers are different, the focal points are different. Our specialty is plastic welding. However, if you want to embed metal into plastic, we can do that. Sometimes we use conductive materials. We've got conductive technologies. We have a smart heating technology that we use for that, where you can heat up and cool down a little cycle. Sometimes it's laser. We find the laser is actually a little too energy dense to do embedding really, really successfully. And sometimes you have to pre-treat the plastic. So I would say separate, probably conversation on that. European representative. For laser plastic welding, I would say we have customers in Europe. We do support them out of the US. We have a distributor for some of our other technologies in Europe, actually in Italy. And so we could maybe have a special consideration for that. It's a great partnership that we have, Chemis Electra. So the answer is sort of, I would say, on that one. Most of our support comes out of the US.
Direct laser application. How does the pressing the melted areas together differ in the weld strength to a normal laser weld interface?
Great question. It is less, for sure. You saw that smoke. Smoke means oxidation. So your plastic's not as whole, I'll say, as in the through transmission laser welding process. I don't know the answer to that off the top of my head. I think you're probably looking closer to the 60 to 70%. Speed matters, what we call open time. So that was actually kind of a slower tool where I think it was like 1.5 seconds. Didn't get that under 2 seconds. That matters for strength. That's a different characteristic, right? You're heating and then pressing instead of heating while you press.
Right. There's no open time.
Very astute question there, man. That's a good one.
Can laser machines be used for removing metallized surface? That's
like a laser ablation, right?
Yeah.
Probably not with these wavelengths.
Yeah.
Yep.
As you guys are thinking of other questions, I'm going to throw up another poll, and this is just feedback for us on this webinar. We want to know how we're doing. So I'm going to launch this. There's 3 quick questions. How was the webinar? And just give us a quick rating. What topics are you interested in for our next training? And then the last one is, do you want us to provide training to your team? We can either do it via webinar like this virtually, so we can present a webinar just for your team. You can expand the reach within your organization, or maybe you're interested in us coming on site and doing plastics joining training there.
All plastics joining.
Yes,
we do.
Whether it's laser or all of the other ones that you saw on one of those earlier slides.
Those questions, just real quick to circle back on that. We want to make sure we answer. If we haven't answered thoroughly, you got our contact info. Shoot us an email. We'd love to nerd out. There absolutely is our lasers to do that. They're very different wavelengths. The 2 wavelengths we've mentioned are specific to getting plastic hot, to melting plastic. So I don't think it's a situation where you could use the same laser to weld the PMMA and then clean it. You would definitely need to use a different wavelength. They're kind of doing different things.
Are other people able to reach the poll? Monty is saying that they can't quite get to it. It
might be a security thing.
Oh yeah, it's possible that your organization isn't allowing you to get to it.
I can't do it.
You can't do it.
What happens if I just while Jason's looking at that, I'll say, yeah, I can get that. Try. I'll say these are some of the best questions that I've seen us have, and we really try to do these webinars interactively, and so this is a really good one. If you stumped us, good job. You get a prize. No. So really good, and if you want to continue the conversation, that's what we're here for. So
I don't know. I have to look into that. There's some people that are able to get to it, but I don't know what I could change.
One cannot, then can't.
Back to the quote. This one. I don't know. Well, if you want to just drop in the chat, like a rating 1 to 5, 5 stars being the best and 1 star being do not recommend. And then I'd take it. If you're interested in training, or if you want to let us know which other technologies you're interested in learning about or other topics, I can put that slide up too. If you wanted to kind of a list of some of the areas of expertise that we have, then we can kind of, if you can't reach the poll, then we'll do it this way. Yeah. Thanks everybody for joining. Are there any other questions that have popped in since I stopped looking at chat? Okay. If you come up with any other questions afterwards and you're like, I should have asked this, then please send us an email. We will send all of you a email with a link to view the recording and a link to download the PDF of all of these slides. And you can just reply to that and we'll take care of you.
Thanks, everyone. Appreciate your time.
Have a great rest of your day.